In this video, we're going to look through a couple of examples of finding centre of masses of composite shapes or shapes with holes in, and look at an example where we're asked for the angle it makes when it's hung from a vertex as well. So in this first one, we're given this shape, this uniform lamina, which means it's got the same density throughout here, which consists of this rectangle and this triangle stuck on the end. We want to think about it this way because those two individual shapes we can think about much more easily than the overall one. So the first thing I do in this question is to split the shape into a rectangular triangle. One's very easy to deal with because this rectangle, well, we know the centre of mass of this rectangle, as long as it's uniform, is going to be bang in the centre of it. Now, it's going to be useful to get a coordinate system going on here. So I'm going to think of P as being my origin, 0, 0 here, and do everything in relation to that. You don't have to choose P as your origin, but this just means I'm not going to have to worry about any negatives as I'm working through. So if that's our origin, then our centre of mass of our rectangle, fairly nicely and obviously, is just going to be 40, bang in the middle of our rectangle. This triangle's a different matter here. Now, there's two ways we can go about finding the centre of mass of this triangle. But I'm going to do that separate to the rest of the question first. So we've got this triangle. Well, what are the coordinates of our various points of this triangle? We know that Q is going to have coordinates 8, 0. R is going to have coordinates 8, 4. And T is going to have coordinates 11, 2. There's two ways we can go about finding the centre of mass of this triangle. The first way is we can find the average of the three coordinates. This, in this case, turns out to not quite be the quickest, but it's definitely the most adaptable to harder triangles. So by the average of the coordinates, I mean, we're saying centre of mass of our triangle is going to be the average of the x-coordinates, so 8 plus 8 plus 11 over 3, and the average of the y-coordinates, which is 0 plus 2 plus 4 over 3. So we're going to end up with 9 and 2 being the centre of mass of our triangle. The other way we could have gone about this, which is marginally quicker in this case, is to say, well, our centre of mass, if we draw a line from the centre of one of our edges to the other vertex, it lies a third of the way from the edge to the other vertex. So given that we know this edge has length 3, if we go 1 to the right, we'll end up there. And fairly obviously the y-coordinate is going to be 2 anyway by symmetry, but it's telling us we're going 1 to the right of our x-coordinates of 8, so it's going to be 9. In cases where you've got isosceles triangles, sorry, my 3 doesn't look much like a 3 there. In the cases where you've got isosceles triangles, it's fairly easy to do this method and can save time. But if you've got nasty coordinates that's not a nice symmetrical triangle, going via the averaging coordinates ways often is the simpler way rather than having to do more geometry. So now we've got the coordinates of centre of mass of both our rectangle and our triangle being 9, 2. We want to find the centre of mass of our overall system. I'll note at this point that we could tell straight away that our y-coordinate of our centre of mass is going to be 2 because it's completely symmetrical about y equals 2. I'm going to pretend it's not obvious just for the sake of showing how we'd approach this anyway, using vectors, although you can set it up separately if you wish. So what are we going to do now? Well, because the lamina is uniform, we can say that the mass of each section is proportional to the density of each section, and we can it's proportional to the area of each section, and therefore we can use the area almost just as a replacement for the mass here. So we're going to have that the area of our rectangle is 4 times 8, or 32, so we're going to have 32 lots of our centre of mass here, which is 40. We're then going to have the area of our triangle is 3 times 4 divided by 2, or 6 lots of our centre of mass of 9, 2, and that's going to be equal to our total area of our overall lamina, which is going to be 32 plus 6, or 38, times by whatever the centre of mass is of this lamina. And by convention, I'm going to write x bar, y bar here. At this point, we just get a nice, easy equation to solve. We have to combine this left-hand side into one vector. If we do that, we're going to get 182, and we're going to get 76 is equal to 38 x bar y bar. And then we're just going to have that x bar y bar is equal to a not particularly nice number on the top, 91 over 19, and 2 as we're expecting there. I might often give centre of mass as coordinates, so this is at 91 over 19, 2. Now actually, if we go back and look at the way this question was worded, it's actually just for two separate bits. It said the distance of the centre of mass from PQ, so that's just how far up are we going, so that's going to be your y coordinate, which is 2, and distance from PQ, distance from PS is just going to be the x coordinate of your centre of mass, which is 91 over 19. So if you get a question like this, state them separately. Otherwise, it's fine to give your centre of mass as 1. Now, we're then asked what angle edge SR makes if we hang the lamina freely from the point S. So what we're talking about is that we've got our centre of mass now, and we know that it's at some point here, 91 over 19, 2. Now, when we hang it freely from S, what's special about the centre of mass is the centre of mass will hang directly below S. So it might be good to twist your head and think about it that way or redraw it, but I think you can get away without redrawing here. And we're being asked the angle of vertical, which is this dashed line I've just drawn in, makes with SR. So we're being asked for this angle here. Now, if we make a nice right angle triangle here, then we can say, well, we know, because we've just found it out, the coordinates of this. So this distance is going to be 2, because we're going from a y coordinate of 4 to a y coordinate of 2. And the x coordinate is 91 over 19. So this now just becomes a pure trig question. And what we're going to do is say that tan theta is equal to opposite over adjacent, and we can just use this to solve for theta, and we'll get 22.7 degrees. So that's the angle that it's making with the vertical there. Okay, I want to look at one more example now where we've got holes in our lamina and see how we can treat these as negative areas. There's other ways of setting this up, but I think the negative's the easiest way of going through it. So in this case, we've got circles. Now, fortunately, circles are easy to tell where those centres of mass will be, but when we've got holes in it gets a bit more complicated. So we're going to think about this as 3 shapes. We've got this big circle, radius 5. We've got this mini circle cut out, radius 2, and this mini circle cut out, radius 1. So when we're setting up our equation here, we can say that we've got the first shape. Again, area is going to be proportional to mass, so we can just think about areas. So the first shape is area 25 pi, and the centre of mass of our big circle is 0, 0. Okay, we're then taking away an area, a circle of radius 2, or area 4 pi, with centre of mass 0, 2, because it's the centre of our circle, so it must be the centre of mass of that circle. Now, because we're taking this away, all I'm going to do, fairly intuitively, is do a subtraction. And we're also taking away this other circle with radius 1, so area pi, which has centre of mass 2, negative 2. And now, again, we can say that's equal to the total area of the shape we're left with, the shape we want, which is going to be 20 pi. And again, we're just going to say that's x bar, y bar, and that's what we want to find. Dividing by pi is a nice, easy thing for us to do, so we might as well divide by pi. And then once we simplify that left-hand side, we get negative 2, negative 6 is equal to 20 x bar, y bar. And you just end up with x bar, y bar is equal to negative 0.1, negative 0.3. Oh, sorry, I've gone off the page there. Negative 0.3. Now, we're asked for coordinates of the centre of mass, so don't give your answers vectors. So the centre of mass is at, I'm making sure I'm stating them as coordinates. I don't want to give them any reason to take marks off me there. And there's my final answer. Thank you.